Welcome to the numerical analysis course. In this lecture, we'll study Python codes to compare Jacobi's versus Gauss Seidel methods to solve system of linear equations. We'll solve this system of linear equations where we have the three equations, and we are going to solve them using Python code we have written for this. You know that the first step is to write the first equation in terms of x1. Everything is on the left and everything else, x1 is on the left and everything else on the right hand side. And similarly x2, the second equation in terms of x2, and the third equation in terms of x3. And then we proceed by first assuming some initial values for x1, x2 and x3. At iteration 0, we normally take them equal to 0. So we assume x1 is equal to 0, x2 is equal to 0 and x3 is equal to 0, and we move on using a Python code. So let's move on to the Python code for this. This one is the code that I have written for Jacobi's method. It's a very simple, a few lines code in which I have assumed the initial values at iteration 0 are assumed to be 0. Right, so initial values at iteration 0 are assumed to be equal to 0. And then we proceed and we go through 10 iterations. We can increase or decrease number of iterations here by writing 5, 6 or any numbers you want. And this a is equal to, this a is actually the implementation of this x1, 12 plus x2 minus 2x3 divided by 5. Divided by 5, 1 over 5 is 0.2. Therefore I have written here 0.2. And then b and c, and then after I have computed these values, I have assigned the values of a, b and c to x1, x2 and x3 once again, so that in the next iteration they are available. The new values are available, and I have also printed the values at each iteration. So let's run this code and see whether it converges to some given roots. So to some roots, to some values of x1, x2 and x3. Right, at iteration number 1, which is 2.4, this is x1, this is x2, and this value is x3. At iteration number 2, x1 becomes 1.1, x2 minus 3, and x3 becomes 1.6. And if we go on, we see that they seem to be converging at iteration number maybe around this. At iteration number 6, we see they seem to be converging. x1 seems to be converging at 1, x2 at minus 2, and x3 at plus 2. And after that, at iteration number 7, 8, 9, and 10, there is no significant change. They seem to be settling themselves at these values 1, minus 3, and plus 2. So if we run even further iterations for this method, maybe if I run 20 iterations of this method, that would be of no use. That would add no good, because the values have already been converged at iteration number 7 or 6. So after that, there is no significant change. So we can write a check here that checks that if the change isn't significant, we break the loop. So this can be homework. So I'm going to give you a homework here. A homework. You need to apply a check that if the values don't change by, if the values change by less than 1%, the loop should break, and the remaining values should not be, and the remaining iterations should not be there. Right, and we could save, and the remaining iterations should not be there. Right, it's okay. So we can avoid these further iterations if we check that if this change is less than 1%, we should break the loop. So this is, I'm leaving this task as a homework for you. Right, and for these two equations, the same three equations, system of linear equations, we have written a code using Gauss Seidel method. This one, Jacobi's method uses the values x1, x2 and x3 computed in the last iteration. However, Gauss Seidel method uses the latest values of x1 and x2 and x3, x1, x2 and x3, whether they are computed in the last iteration or they are in the recent iteration. So instead of having a, b, c here that we had in case of Jacobi's method, we have x1, x2 and x3 here, because when we are executing this x2, the second statement, the latest value of x1 would be the value of x1 that we would have computed in the same iteration. So we would use the recent value, the latest value, the most recent value. So this is the difference between Gauss Seidel and Jacobi's method. And when we implement this x3, we'll use x1 and x2 computed in the same iteration, not of the previous iteration. So this is the difference between these two methods. And if we run it for 7 iterations, it runs like this, and it seems to be converging at 1 minus 2 and 1 minus 3 and plus 2 at iteration number 3 very quickly, quicker than the Jacobi's method, right? Iteration number 4, and then we don't see any significant change. If we run this for even higher number of iterations, maybe for 15 iterations or maybe for 20 iterations, you see that won't add much to it, because the values are somehow they are settled. So actually they settled at iteration number very early. They settled at iteration number 3 or iteration number 4, and then they didn't change much. So you can apply the same check here. So the homework goes on, and you need to apply the same check here too, to break the loop if the change is less than 1%. So this is your homework for these two Python codes, the code for Gauss Seidel method and the code for Jacobi's method. I have already shared Jacobi's method, the code for Jacobi's method in the group, and soon I'll be sharing this Gauss Seidel method, this code too. Right, so that's all for this lecture. Thank you.